we always do it this time. I go for mine, I get to shine. Now throw your hands up in the sky. I go for mine, I get to shine. Now throw your hands up in the sky.
Oh, welcome back, ladies and gentlemen, to another edition of our Flipped Classroom. We're going to talk about a very nice topic tonight, perhaps shooting for a record-setting performance as far as for the shortest video tonight. And our topic is logarithmic differentiation. What I've done is I've presented 4 different functions on the screen here that I want to take the derivative of, and some of these are going to be very easy, some of these are going to be very challenging, and in fact, we should know how to take the derivative of at least 3 out of the 4 quite handily, and I'd encourage you to hit that pause button right now and go ahead and take the derivative of each one of these functions and then maybe try to figure out which one we haven't really covered yet. Okay, so welcome back. Hopefully you were able to hit the pause button and tackle 3 of these. The first one was perhaps my favorite. I recognize that e to the e is simply a constant, and so the derivative of any constant is simply 0. So that was my favorite one of the batch. And then number 2 here was another friendly function. We know that the derivative of e to the u, let's see, I'll make this note right here, e to the u, his derivative is simply e to the u times du, and this is a much simpler version of that. Derivative of e to the x is simply e to the x. The derivative of x to the e is a lot like the derivative of x squared, where we're going to use our power rule. So the derivative here is simply e times x to the e minus 1 power. The key there is that I want you to pay attention to is you have a variable as your base being raised to a constant power, okay? Anytime you have that combination, it's always going to be power rule. Notice variable in the base, constant in the exponent. What we're going to do here in number 4 is everything gets turned upside down. And the reason things are getting turned upside down is because we've got a variable in the base and a variable in the exponent. And up until this point of our calculus career, we have not seen that. And so that's where logarithmic differentiation is going to come into play, is when we have a variable raised to a variable. And I just want to reiterate that one more time. When do we use this method called logarithmic differentiation? Okay, when do we use it? Whenever you have a variable somewhere in your base and then you also have that same variable hidden in your exponent, that's when we're going to employ a technique called logarithmic differentiation. And you're probably wondering to yourself, why do we call it that? I didn't see any logs in that last problem. Well, we're going to introduce our own logs here in the next slide. So, we're in the middle of a test and we're kind of humming along, and then all of a sudden we encounter a problem here that looks like number 1, where they've given us a function y equals x raised to the x power. It's a very exciting function. What we're going to do here is we are going to take, okay, step number 1 here is we are going to take the natural log of both sides, okay, which is certainly a legal move. It may not make sense right now, but of course, whatever you do to one side, as long as I do the same thing to the other side, it's certainly a legal move, if not a smart move anyway. And perhaps some of you can see the advantage of that, what's coming on down the road. We're going to take advantage of a log property that says that the exponent is allowed to become the coefficient. Okay, so I could rewrite the right side as x times the natural log of x. All we're doing is grabbing this rascal here and sliding him down into the coefficients position. Now we are ready to do some serious calculus here and take the derivative of both sides. The left side is very interesting. Normally when you take the natural log's derivative, it's du over u. So in this case, I'm going to say y prime divided by y itself. And then on the right side, I've got to use some product rule. Okay, make a note to yourself that we're definitely using some product rule. First times the derivative of the second plus the second times the derivative of the first. Okay, and we're very, very close to finishing this one up. We could say that what I'm going to do is I'm going to multiply both sides by y over 1. Okay, on the left side, that would then give me y prime equals, let's see, square brackets, 1 plus the natural log of x times the y that I was multiplying both sides by. And all they're going to do now is they don't want you to express the derivative in terms of both x and y. They want you to strictly express that derivative in terms of x only. So what I'm going to do is I'm going to substitute, if you go back and look at the original equation, they said y is equivalent to x to the x power. So I'm just making that little substitution for y. I'm writing it as x to the x. And so, ladies and gentlemen, here's our final answer for that derivative. Very ugly derivative, certainly messier than the other three examples we did on the previous page that were so elementary and simple. Okay, again, we're going for our record-setting performance of shortest video of the year, and here's our last example for the night. And we're humming along in the middle of an exam, and we're wondering what's going to trigger me into thinking to use this technique of logarithmic differentiation. And again, we want to reiterate that not only do we have a variable in the base, but we also have a variable hidden up there in that exponent. We've got the x here and then the x up there. So right away, we said we're going to take the natural log of both sides right away. Okay, and so it's the quantity x plus 2 being raised to the 1 over x power. We're then going to take advantage of a very nice log property that says the exponent can slide down into the position of coefficient. And once we express it as such, we're now ready to actually start doing some calculus here. Derivative of the left side is y prime over y. And then the product rule gets a little messier. We've got the first times the derivative of the second function plus the second function times, let's see if I can squeeze this in, the derivative of that first function would be negative x to the negative 2 power. Okay, so we just squeezed it in there. I'm tempted to try to clean this up a little bit. 1 over x, quantity x plus 2, if I multiply those two guys together, actually it's a minus the natural log of x plus 2 all over x squared. So we're just cleaning it up a little bit. Of course, that last term, since it had a negative exponent, we could throw it in the denominator. And now perhaps one of the trickiest steps here is that we're going to multiply both sides by y in order to isolate that y prime. Always make good use of our square brackets here. I can say x squared plus 2x now, minus the natural log of x plus 2 all over x squared, times the y that I just multiplied over. And then one last step is we're going to substitute, because we don't want to express our derivative in terms of both x and y. We want to express it strictly in terms of x and x only. So what I'm going to do is I'm going to substitute the original function in for that y. And probably there's a part of you deep down inside that wishes we could clean this one up a little bit nicer and maybe make it look a little sweeter, more simplified. But I tell you what, it is what it is. That's as pretty as it's going to get. And the good news is it's still capable of finding the slope of the original curve at any point we want. So it still accomplishes what any derivative sets out to accomplish. So hopefully that helps. There's our lesson on logarithmic differentiation. Keep your eyes peeled. You never know when you'll see a variable raised to a variable.